Bismillahirrahmanirrahim. Assalamu alaikum. For the last few weeks, we have been discussing basic fluid kinematics, and we are basically focused on the Bernoulli equation B plus half rho V square plus gamma Z equals to constant along the streamline. I hope for now you have developed a very good sense of the three terms in the Bernoulli equation, that is the static pressure, the dynamic pressure, and the hydrostatic pressure. And we also discussed in the last class what is meant by the static pressure, what is the meaning of this dynamic pressure, and what is the meaning of this hydrostatic pressure. We also discussed that the sum of the static pressure and the dynamic pressure is called the stagnation pressure, and how it is measured, how we measure the static pressure using the static tube, and how we measure the stagnation pressure using the pitted tube, and how we combine the two tubes to measure the two pressure for us. That can help us to calculate velocity of the fluid or the velocity of the body. And we discussed the application of the pitted static tube in the aircraft speed measurement. Today we are going to further discuss in detail some other applications of the Bernoulli equation. The first of that is free jet. Any idea about this term free jets?
No, sir.
Free jet is a flow under the action of the gravity, in which you are not giving some air. Like let's say I have this tank that is filled with fluid or water. This is the free surface. And there is suddenly some hole is created in this tank. Let's say at this point, there is a rupture and there is a hole created. What will happen?
Water will
Fluid
come
will
out.
come out.
Water will start coming out. The fluid will come outside under the action of what? Gravity. It will not be aided or it will not be forced flow. It will be natural flow, right? There may be a rupture at the bottom here, and the flow will be under the action of the gravity, right? So this sort of flow is called free jet. Clear?
Yes, sir.
So we discuss how we apply Bernoulli equation to the free jet situation by considering this diagram, and we'll discuss in detail. So consider this figure here. So in free jet, initially the fluid is at rest, okay, and when there is a sudden opening or a hole, the fluid starts to flow from that hole. According to the Bernoulli equation, we can write Bernoulli equation at any of these points, point 1, point 2, point 3. According to Bernoulli equation, the sum of the three pressure at all these points should be equal to the total pressure should be equal to the constant. That is the if I write Bernoulli equation at point 1, it should be equal to the Bernoulli equation at point 2 and should be equal to the Bernoulli equation at point 3, right?
Yes, sir.
So if I write P1 plus half rho V1 square at point 1 plus gamma Z1. This is equal to some constant C, which is the total pressure. And at point 2, it should be also equal to the total pressure, that is P2 plus half rho V2 square plus gamma Z2 equal to constant, right? So in other words, P1 plus half rho V1 square plus gamma Z1 should be equal to P2 plus half rho V2 square plus gamma Z2. Now we can apply some simplifications on this. What simplifications can be applied?
Sir, V1 equal to 0
Because point 1 is located on a free surface, and at the free surface the pressure is the atmospheric pressure. This pressure would be equal to the P atmosphere, and if we are using gauge readings, then this atmospheric pressure should be equal to
0.
0. So basically P1 is 0. So we can omit this. What about P2?
Rho GH.
Now that term is already accommodated here. Abdullah, that term is already here, gamma Z2. This P2 is static pressure. Okay, don't confuse it with the hydrostatic pressure. What about this P2?
ये भी 0 है.
Yes, because the opening is into the atmosphere again, right?
जी.
Like let's assume at this point the fluid is interacting with the atmosphere. At this point the fluid is interacting with the atmosphere. So along this horizontal line the pressure should be same.
0.
So this P2 would be 0. About gamma Z1 and gamma Z2. This depends on the reference. Like I say, I am placing my reference line here at point 2. This is my reference line. So at reference, the elevation would be
0.
Z2 is 0.
0.
So gamma Z2 is 0. What about Z1? I will measure it from my reference line and it would be equal to H. Z1 equal to H. So this is gamma H. Clear?
Yes, sir.
Now about V1 and V2. About V1, you can say it is 0. It is approximately equal to 0. Why? किसी का mic on है जिसको please off कर लेंगे. So V1 is approximately equal to 0. Why? Because considering the area of the one, that is A1, this area, as compared to the area of the hole, this point 2, the velocity at point 2 would be much greater than velocity at point 1. That is V2 would be very large as compared to V1. So we can approximate V1 to 0 because its effect would be negligible. Its contribution in the pressure equation would be negligible. Clear?
Yes, sir.
So this is 0. So at the end we get gamma H equals to half rho V2 square. And if V2 is equal to V, then we can write V equals to 2 gamma H by rho under root, or we can write V equals to under root 2
GH.
H, which is the basically free fall velocity. You would have already studied this.
Yes, sir.
So in free jets, the velocity is equal to the free fall velocity, which is 2gh, the elevation from which the flow is taking place. Clear?
Yes, sir.
The other situation for the free jet can be the horizontal flow. This was the vertical direction. You can also do this in the horizontal direction, like this. If the flow is, let's say, this is the tank, this is the hole, and this is free surface, and the flow is in this direction now. This is our point 1. This is point 2. Now again, can we write the Bernoulli equation at the 2 points?
Yes, sir.
The Bernoulli equation would be equal to P1 plus half rho V1 square. So bad writing. Square plus gamma Z1 equals to P2 plus half rho V2 square plus gamma Z2. Now again, considering the simplifications, P1 would be 0, P2 would be 0, V1 would be 0 because V2 is much greater than V1. Again, if we replace reference at point 2, then Z2 would be 0 and Z1 would be H. What if we place reference here at the bottom of the tank? And I say Z2 is capital H and Z1 is this small h. Will there be any difference in the equation?
Yes, sir. Sir, वो height की जगह capital H minus H1 आएगा.
Basically, again, we will be considering only this height, which is the free fall height, जहाँ से fluid ने fall करना है. So let's say H dash, this H dash, right? So there will be no difference in the equation because it will only be considering the difference of the two heights, two elevations. Clear? So gamma H equals to half rho V square if the velocity at the exit is V plus gamma capital H. Or we can write gamma H minus capital H into 2 divided by rho under root equal to the velocity. Further simplification, we can write 2g velocity equal to under root 2g h minus h. So there is no difference in the two equations. They remain same for either it is vertical flow or it is the horizontal flow. So in case of free jets, the velocity is measured by the free fall velocity, that is 2g under root 2gh. Clear? Any question in that?
Clear, sir.
Okay, then we move further in this topic. So these are the simplifications in the free jet. Now there is one error in the velocity measured at the free jet or the free jet velocity. That is what happens usually. If I have a tank like this, and this is the hole in the tank. This tank is filled with water like this. When the water will flow from this hole, the diameter of the jet of water will be less than this diameter of the hole, right? This is the diameter of the hole. Let me draw it like this. Right, and this is the diameter of the water jet. So diameter of the hole is greater than the diameter of the jet. This is why, because the fluid does not have the ability to follow the sharp corners. It cannot exactly like it will not be able to follow a path like this, that it comes like this and then it moves like this. It follows a curved path. So the fluid does not have the ability to follow the sharp corners. Therefore, the diameter of the jet generated from the free hole or the hole is less than the diameter of the hole. So what happens? So what would be the result of this? Any idea?
Sir, वो final calculation में error आएगा.
इस किस्म का एरर आएगा. जो velocity हम calculate करें, that would be erroneous.
Yes, sir.
Right? Because smaller the area, greater is the velocity.
Velocity.
Area and velocity are inversely related. Right?
Yes, sir.
So smaller the area, greater will be the velocity. So if we are calculating our velocity based on the whole area or the whole diameter, what we will be doing, we'll be predicting less velocity as it will be actually. We'll be predicting less velocity as compared to the actual velocity there.
Yes, sir.
Right? So what we do, we apply a contraction factor, contraction parameter. We use a correction factor, which we call as CC, which is the ratio of the area of jet divided by the area of hole. And if the hole and the jet are circular, we can also write it as diameter of the jet divided by diameter of the hole square. Clear?
Yes, sir.
This effect is called Vanna contracta effect, and this CC is called contraction parameter. So we multiply the resulting velocity with the contraction. Sorry, we divide the resulting velocity with contraction parameter. Clear?
Yes, sir.
And contraction parameters can be measured experimentally. Contraction parameters that is measured experimentally. How experimentally? You will perform this experiment in fluid mechanics lab. Depending upon the hole geometry, you can know the area of the hole. You can know the diameter of the hole. You can simply measure that. Once that is done, then you can measure the diameter of the jet using some technique in the lab. And simply by calculating the ratio of the two diameters, you can get the contraction parameter. For different geometries, it is different. For example, if the hole is a channel like this in the figure on the top right side, CC would be equal to 1 because the diameter of the hole and the diameter of jet is same. In another case, when there is sharp corner, the contraction parameter would be 0.61, which means that the hole would be jet would be 61% of the hole diameter. Clear? And in another case, when the channel is not that much, the channel is short but is also elongated along the path, then the contraction parameter is again 0.61 because there is a sharp corner. So for sharp corners or edges, there the contraction parameter is 0.61, and for the corners in which there is sharpness does not include, it is 0.50, like the figure in the bottom right. Clear?
सर किस चीज से डिवाइड करना होता है सीसी को?
CC is the contraction parameter, it's the correction.
नहीं सर, सर वो किस चीज पे करते हैं? एक वेलोसिटी के साथ डिवाइड करते हैं?
I can just, you will calculate velocity based on this equation, v equals to under root
अच्छा, इसके ऊपर बस डिवाइड कर देंगे
2gh, right? And you need, now this velocity is based on the fact that you are using this reference to as like that the fluid is exactly at this path. You are using like this thing as h, but in fact this is not h is this, right? So will you
किधर से
know,
आ रही है आपको आवाज?
right?
कर्व बन रही है आउटलेट पे, तो उसकी रेडियस को फाइनल जो हमारे पास हाइट आ रही है फाइनल इक्वेशन में अंडर रूट 2gh उसके साथ ऐड करके तो हम वो एरर तो फिनिश हो सकता है।
वो आप राइटली सेट के आप उसको उस इक्वेशन के अंदर या तो इंक्लूड कर लें या बाद में आप करेक्शन अप्लाइड कर लें, दोनों तरीके ठीक है, उसमें कोई ऐसा इशू नहीं है। या तो आप पहले से ज्योमेट्री को समझ लें कि अच्छा जी मेरे जो जेट है उसका डायमीटर इस तरह से डिक्रीज होगा, तो आई कैन करेक्ट इट इन द इक्वेशन, और यहाँ बाद में वेलोसिटी कैलकुलेट करने के बाद उसके ऊपर करेक्शन अप्लाई कर लें, ठीक।
यस सर।
The next application of the Bernoulli equation, any question in the free jet problem? कोई फ्री जेट की एप्लीकेशन के हवाले से कोई आपको इशू? हम इसके प्रॉब्लम्स बाद में सॉल्व करेंगे, एक बार हम उसकी सारी एप्लीकेशंस देख लें। क्लियर?
Yes, sir.
Okay, जी. The next application of the Bernoulli equation is in the confined flows. Confined flows are like, any idea about confined flows?
रोज
रोज आपका ताल्लुक है इनके साथ रोजमर्रा का। Flow in any pipe like this is a confined flow, right? The flow will enter from one side and the flow will exit from the other side. Clear? So for such flows, what you assume is that for confined flows, this is a confined flow application. So I write it confined. What happens in confined flow? that amount of mass entering at one point should be equal to the amount of mass exiting at the other point, right? That is m dot
Yes, sir.
1 should be mass flow rate at point 1 should be equal to the mass flow rate at point 2. Clear? So the law of conservation of mass should hold for the confined flows. So let's say if this was the initial mass we were considering. This is the initial mass, and after time t, it should move. The same amount of mass should be replaced by another amount of mass. Let's say it has moved the some distance s. That distance s would be equal to
VT.
velocity into delta t. Clear? And if I want to calculate you this volume V1 and this volume V2, how will you calculate this volume V1 and V2? If this is S1 is V1 into delta T and S2 is V2.
Cross-sectional area multiplied by V1 delta T or cross-sectional area multiplied by V2 delta T.
Yes, V1 would be equal to A1 into S1, right?
Sir.
And it should be equal to V1, A1, V1, sorry, A1, V1 delta T, and V2 would be equal to A2 into S2, or it should be equal to A2 V2 delta T, right? Now if I divide V1 by T, then it would be, if I take this V1 by delta T would be equal to
Volume
A1
flow rate.
V1, and this we write as equal to Q1, which is basically the volume flow rate. This is volume flow rate meter cube per second or feet cube per second. Clear? Similarly,
Yes,
V2
sir.
by delta T equals to A2 into V2 and represented by Q2. So volume flow rate is represented by Q in fluid mechanics, and this is Q2. Clear?
Yes, sir.
Now, what if I write the Bernoulli equation between 2 points? I would be writing P1 plus half P1 plus half rho V1 square plus gamma Z1 equal to P2 plus half rho V2 square plus gamma Z2. So what about P1? We don't know. There will be some value for P1 because it is not a free surface now, right?
Yes, sir.
V1 will have some value because it is
Yes,
in a
sir.
confined flow. P2 will have some value. V2 will have some value. What about Z1 and Z2?
Z1 दोनों equally होंगे सर.
Because in a center line फ्लो हम सेंटर लाइन, ये पॉइंट सेंटर लाइन पे बेस कर रहे होंगे, एंड along a center line there will be no change in elevation, so z1 should be equal to z2, can cancel them out. Clear?
Yes, sir.
So p1 plus half rho v1 square equals to p2 plus half rho v2 square. Now what we are seeing is that we have basically, if we know p1, if we know v1, if we know p2, then we can calculate v2. But normally is the scenario that there are two unknowns. Let's say we can measure p1, we can measure p2, but we cannot measure v1 and v2. So we need an additional equation. From where do we have that additional equation?
Volume flow rate.
Yes, we know that mass flow rate is fixed for these flows. M dot 1 should be equal to M dot 2, and we can write mass is equal to, mass is basically
Rho V.
density into volume, right? And
Yes,
if
sir.
I want to write mass flow rate, that would be equal to M dot divided by, M dot, which is basically M divided by T. So that would be equal to rho Q. Clear?
Yes, sir.
So M1 is equal to rho into volume 1, M dot 1 equals to rho into Q1. And according to law of conservation of mass, M dot 1 should be equal to M dot 2, which means rho Q1 should be equal to rho, Q2, which means Q1 should be equal to Q2, because density is fixed, it's a constant. We are considering incompressible flows. When we are applying Bernoulli equation, we are considering that there are no viscous effects and the flow is incompressible. So for incompressible flows, mass flow rate as well as the volume flow rate is fixed, is constant. There is no change in mass, there is no change in volume flow rate as well. Clear? This means A1 V1 equals to A2 V2, or we can write V1 equal to A2 V2 by A1. Right?
Yes, sir. सर ये P1 P2 कैंसिल आउट क्यों नहीं हो रहा है? ये दोनों तो इक्वली गए हैं एक सेंटर लाइन पे.
Oh, no. We can, I have drawn a very simple geometry. Let's say maybe the confined flow is like in a pipe like this. We have like pipe like this. Now this is point 1. This is point 2. Will P1 and P2 be same along the center line? Here velocity would be less, V1 would be less than V2. So the major pressure would be static pressure. In this point, the velocity is increasing, which means there is some static pressure would be converting into dynamic pressure. So P2 would be less than P1. Clear? But the total
लेकिन
pressure would be same.
सर आपने कहा था स्टैटिक फ्रिक्शन होगी और जो फोर्स होगी, सॉरी, जो स्टैटिक प्रेशर होगा तो वो कांस्टेंट थ्रू आउट द जर्नी होगा.
अगर आपका
कन्वर्जेंट
फ्लो इन उसमें मैंने अगेन जब भी हमने बात की तो हमने बात की देयर शुड बी सम रिस्ट्रिक्शंस. If this is the scenario, uniform area, there is no change in area, the static pressure will remain throughout the same. Throughout जो वो same रहेगा. But if there is change in geometry of the flow, if there is change in the geometry of the pipe, or the channel, then there will be variation in the static pressure as well as the dynamic pressure. Clear?
Yes, sir.
उस वक्त तो हमने ज्योमेट्रीज डिस्कस नहीं की थी ना, फ्लो ज्योमेट्रीज क्या है, तो शायद वो जेनेरिकली बात करते हुए मैंने आपसे कहा होगा ठीक है जी ये इसी तरह होगा, बट व्हेन द ज्योमेट्री ऑफ द फ्लो विल चेंज द स्टैटिक प्रेशर विल चेंज. ठीक है,
सही सर.
so we can write V1 equals to A2 V2 by A1. Using this equation we can replace V1 here with this form, so we can write P2 minus, I'm just rewriting this equation here to get the velocity. I'm writing P2 minus P1 into 2 divided by rho equal to V1 square minus V2 square, right? Or you can replace V1 by A2 square V2 square by A1 square minus V2 square. Or we can write it as A2 by A1 whole square minus 1 closing larger bracket and V2 square. Or we can write it as that V2 is basically equal to 2 P2 minus P1 divided by rho into A2 by A1 square minus 1 and then this whole square root. Clear? Is it clear?
Yes, sir.
So if we get V2, we can calculate V1 using this form. So we'll have V1, V2, and our flow will be very defined. So velocity is a basic component in defining any flow. If we know velocity, we can calculate volume flow rate, we can calculate mass flow rate, we can calculate forces, we can calculate the energy, whatever the parameter is required to us by having knowledge about the velocity. So this is how we calculate velocity for the confined flows using Bernoulli equation. Any question in that?
प्रेशर सर एक्सपेरिमेंटली मालूम करेंगे.
This P2 and P1 can be measured from the static tube. You can have knowledge of this P2 and P1 from the static tube, or in a reverse, we can be like, we may be interested in, okay, I want my fluid to flow with this much velocity, then how much static pressure will it be experiencing? How much static pressure will be there? So in a reverse direction, we can use this equation to calculate the pressure as well. Clear?
Yes, sir.
We solve a simple problem in which we are basically applying the both concept, that is the free jet application and the confined flow application. In this problem, we have, let me take it there. So we have air that is enclosed in a tank, and it steadily flow from this tank through a nozzle of diameter D. This is the nozzle of diameter D, which is 0.03 meters. And then it exits to the atmosphere from a nozzle of diameter 0.01 meters. The pressure in the tank remains constant at 3 kilopascal. There is some mechanism that we have kept this pressure constant in the tank at 3 kilopascals, and the atmospheric conditions are standard pressure and temperature, that is 15 degrees Celsius, and pressure is 1 bar. You need to determine the flow rate Q and the pressure in the hose at point 2. You need to calculate P2 and you need to calculate the flow rate Q. So any ideas, any suggestions that how we should proceed with this problem? We are interested in calculating this flow rate and the pressure at point 2. That is, we want to calculate P2 and we want to calculate Q2 or Q3, whatever, because they would be same. Q2 would be equal to Q3. We are interested in calculating this. So any ideas? How we should proceed with that?
वेलोसिटी निकालनी होगी.
Yes, we need to find velocities, and how will you get velocity?
सर जी तो नहीं है इसके अंदर, तो बस बर्नौली इक्वेशन ही इस्तेमाल करेंगे वो पहले दो टर्म्स के साथ.
So I write Bernoulli equation between
Density
any
भी
two
same है.
points or any all of these 3 points. I can write P1 plus half rho V1 square. I am not writing gamma z term because it is constant throughout, so it will cancel out in all 3 points. This should be equal to P3 plus half rho V3 square, right?
जी सर.
So what about P1? We are given that it is 3 kilopascals. What about V1?
रेस्ट से स्टार्ट होगी.
Because it's a large tank and velocity at point 1 as compared to velocity at point 2 and point 3 would be very small, so we can neglect this velocity, right?
यस सर.
What about P3?
सर वो फाइंड करनी है.
P3
P3
is
अच्छा P3
charging into the atmosphere. It's a jet, right?
जी.
So P3 would be atmospheric pressure.
1 bar.
And on a gauge scale it is 0. Clear?
सर लेकिन तो इन्हें प्रेशर 1 बार क्यों दिया हुआ है वैसे ही?
ये 1 बार कौन सा प्रेशर है भाई?
एटमॉस्फेयर ही है, लेकिन तो इन्हें इग्नोर करना होता है इस तरह.
It is the absolute value.
Atmosphere.
सही.
Okay,
ओके.
so we can write V3 equals to 2P1 divided by rho under root. So what is P1? 3 kilopascals. What is rho?
तो फ्लूइड बताया. एयर.
Air is a gas,
जी.
and for gases, how we calculate density?
Ideal gas equation.
Yes. So what is the ideal gas equation?
सर पीवी गिवन है और वॉल्यूम भी गिवन है. पीवी इज इक्वल एम आर डी
Rho
Volume
equals to P by RT. ऐसा ही है? So we can write P1, which is known pressure, by R by T1. P1 is 3 kilopascals, and in this equation we use P1 should be the absolute value, and 3 kilopascals is the gauge value. So we need to write 3 plus 101 kilopascals, right, to make it the absolute value. For air, the ideal gas constant R is 286.9. Newton meter per kg Kelvin. The units are Newton meter. These are in kilopascals. This is in Newton meter per kg Kelvin.
Sir?
Yes.
Like 1 bar तो like 100,000 ही होता है ना?
बार की कन्वर्जन क्या है किलोपास्कल के साथ?
तो फिर चेक कर लेता हूँ फिर से, लेकिन एग्जैक्ट नहीं होती है कि लाइक 100 के पी है, ये 101 होता है ये.
101 के इक्विवेलेंट ही होता है.
Okay.
101.325.
Basically, the standard atmosphere is 1.01 bar.
Right. इसलिए हमने 1 बार कहा.
उसने सिंप्लिसिटी के लिए 1 बार लिखा हुआ है, ठीक है. तो that should not be a confusion. 0.01 को जैसे हम 101.3 किलोपास्कल्स लिखते हैं
जी.
एटमॉस्फेयर जो स्टैंडर्ड, अभी हमने 101 यूज किया.
Okay.
ठीक है. That should not be a problem. T should be in kelvins, so it should be 15 plus 273. And the units are Kelvin. So quickly calculate rho, that would be equal to, calculate rho 104 divided by 286.9 multiplied by 15 plus 273 comes up to be point 0.0012, but the unit would be Kelvin is gone with this. It would be not kg or not the units, kg per meter cube. So 1.26 sorry, 1.26 kg per meter cube would be unit if we adjust that kilopascal. Okay. Clear? You can work out with the
Yes, sir.
units. Now we can calculate V3 easily. V3 would be equal to 2 into 3 divided by density, which is 1.26, and square root of this. V3 would be
2.18.
under root of 2 into, pressure should be in pascals, so 3 multiplied by 1000 divided by, units का आपने ख्याल रखना है, pressure should be in pascals, ठीक है, 1.26. Now you take the square root. Square root of 2 multiplied by 3 multiplied by 1000 divided by 1.26. It comes up to be 69 meter per second. Clear? So we can calculate the flow rate easily now. Q, which would be equal to Q3 or Q2, and that should be equal to area of 3 into
velocity.
Area at point 3 would be equal to pi d square by 4, pi multiplied by d, which is 0.01 square divided by 4 multiplied by 69. So 3.14 multiplied by 0.01 square multiplied by 69 divided by 4. That comes out to be 0.0054 meter cube per second. Now, what about P2? How to calculate P2?
सर भी सेम ही होगा ना, जो P1 पे और P2 पे सेम ही होगा।
No.
जैसे
Again, there
हमारे
is
पास
a change in geometry. यहाँ पे कोई फ्लो नहीं हो रहा, यहाँ पे हम क्या कह रहे हैं, फ्लो इज स्टैटिक। यहाँ पे वेलोसिटी है, एरिया चेंज हो रहा है, देयर विल बी चेंज इन P2।
फिर से Bernoulli इक्वेशन।
सो वी राइट अगेन। जी जी, किसी और क्वेश्चन है इसमें? We write Bernoulli equation between point 1 and 2 in order to have knowledge about P2. What would be P2? Okay, so P1, I am not writing velocity, I am not writing the hydrostatic term, I am not writing the dynamic pressure and the hydrostatic pressure, because you know that it is equal to 0. V1 is 0 and C1 is fixed. P1 should be equal to, at point 2, there will be pressure P2 and there will be some dynamic pressure as well, half rho V2 square, right? So we can see that P2 is equal to P1 minus half rho V2 square. So we need V2 in order to calculate P2. So what is V2?
सर
फ्लो
फ्लो रेट
रेट
सेम है तो
सेम
उससे कैलकुलेट कर लेंगे।
So flow rate is fixed. We can write Q equals
A1
to
V1 करके
not A1 V1, Q equals to A2.
वही सर A V करके।
Okay, so V2 would be equal to Q divided by A2. Which is A2 is pi d square by 4, which is 4 times Q divided by pi into 0.03 square. So we'll have 4 into 1 divided by 3.14 multiplied by 0.03 square. Comes up to be 7.67 meter per second. So V2 is 7.67 meter per second. Right?
सर ये वॉल्यूम फ्लो रेट हमें क्यों नहीं कि कांस्टेंट रहेगा, क्योंकि एयर एयर तो कंप्रेसिबल है, तो हम ये एज्यूम करें कि कांस्टेंट है।
मेरे भाई, अगर आप ये assume नहीं कर रहे कि इनकम्प्रेसिबल फ्लो है, तो फिर तो आप बर्नौली इक्वेशन अप्लाई नहीं कर सकते। फिर तो ये प्रॉब्लम स्टार्ट से ही हम गलत कर रहे हैं, राइट? फिर तो हमने assumption ही वायलेट कर दी ना, जो डे 1 से मैं पढ़ाता आ रहा हूँ कि जी बर्नौली इक्वेशन के अंदर आपने फ्लो जो है वो इनकम्प्रेसिबल एज्यूम करना है। तो अगर आप मुझे ये कहेंगे कि फ्लो कंप्रेसिबल है, तो फिर तो बर्नौली इक्वेशन मैंने गलत अप्लाई कर दी। ठीक है?
यस सर।
Okay. So now we can calculate P2 simply by P1 minus half rho V square. So P2 is 3 into 1000. Use pressure in pascals because we are using velocities in meter per second square and density in kg per meter cube. Half into what is rho 1.26 into V2 square, which is 7.67 square. Half V2. So multiply by 1000 minus 0.5 into 1.26 into 7.67 square. That is 2962.93, which is 2963 newtons per meter cube, newtons per meter square, 2963 Newton per meter square, or 2.96 kilopascals. So that 0.4 kilopascals has converted into what? The pressure at point 1 is 3 kilopascals and the pressure at point 2 is 2.96 kilopascal. There is a difference of 0.04 kilopascals. So what has happened to that 0.04 kilopascals?
Dynamic pressure.
increase करके
That is the velocity at point 2. That is converted to dynamic pressure at this location. The velocity is due to change of that 0.04 kilopascal into the dynamic pressure. Clear?
Yes, sir.
Yes, sir.
At point 3, we are telling that, okay, the pressure at point 3 is 0. So we can see that the velocity at point 3 is much greater than velocity at point 2, which means all of the static pressure at point 3 is converted into dynamic pressure.
Dynamic pressure.
Clear?
Yes, sir.
So this is how we apply Bernoulli equation to different flow situations. Any question in this problem?
No, sir.
Okay, these are your homework problems. They are very similar to the problem we have solved. Their difficulty level is almost equivalent to that, or there should be like some problems that are a bit challenging, but you should solve them and we can discuss them. And whenever you want to discuss if you solve them. And there is a reading assignment for you as well. There's a topic in your book that is restriction on use of the Bernoulli equation. There are some restrictions on the use of the Bernoulli equation. You should study this topic and we will discuss it in the next class, inshallah. Okay. The next application of the Bernoulli equation is the flow rate measurement.
Sir,
ब्रेक भी करनी है अभी हमारी बहुत सी क्लासेस रहती हैं बीच में मुझे फिर वो भी करनी पड़ेंगी इफ आई वांट कि मैं इन्हीं क्लासेस में उनको कंपनसेट करके जो है वो जल्दी से नहीं तो मुझे फिर फ्राइडे वाली मेकअप्स भी लेनी है पिछली
पढ़ाएं सर पढ़ाएं
ठीक है सो वी कैन जस्ट कंटिन्यू विद दैट कि हम इसी के अंदर उनको कंपनसेट करने की कोशिश करें ओके जी फ्लो रेट मेजरमेंट flow rate measurement is another application of the Bernoulli equation. How we can measure flow rate is a very simple. Okay, I ask you a question, simple enough question. आपने वाटर टैप खोला घर में अपने, ठीक है जी, एक फिक्स रेट पे खोल के उसको रोक दिया. आई आस्क यू यार मुझे फ्लो रेट बताओ इसका कि किस फ्लो रेट से ये वाटर जो आपको दे रही है. मैंने अगर 1 लीटर पानी लिया तो कितने टाइम में मुझे मिलेगा इसमें से, तो आप कैसे मेजर करके बताएंगे?
सर जो टेप की एरिया हमने खोला है तो उसको फाइंड करेंगे पहले, फिर वो जितनी एलिवेशन से पानी आ रहा है ऊपर से वो भी फाइंड करना होगा.
अब मेरे दोस्त जो हैं वो बिल्कुल बर्नौली इक्वेशन के उसमें रंग में ढल चुके हैं. अगर मैं होता तो मैं क्या करता, मैं एक कंटेनर लेता जिसकी वॉल्यूम मुझे नोन,
उससे मालूम कर सकते हैं.
जिसकी वॉल्यूम मुझे नोन है, वो कंटेनर में उसके नीचे रखता, साथ में स्टॉप वॉच ऑन करता, देखता कितने टाइम में इसने ये कंटेनर फिल किया, मैं आपको फ्लो रेट बता देता. दैट्स द मोस्ट सिंपल वे टू मेजर फ्लो रेट. बट नॉर्मली ये तो ऐसी सिचुएशन है जहां पे हम फ्लो को कंटेनर के अंदर लेके आ सकते हैं, लिक्विड फिल कर सकते हैं, बट देयर कैन बी सिचुएशन जहां फ्लो कन्फाइंड है, जहां पे यू कैन नॉट लाइक एक्चुअली डिस्चार्ज द फ्लो फ्रॉम द पाइपलाइन और फिर इसकी क्वांटिटी फिल करें और टाइम नोट करें. In that case, what will you do? In that case, you remember the simple principle that change in area causes change in velocity. Continuity equation. That if there is a change in area, there will be change in velocity. So based on that, we can have different flow rate measurement devices. Let's say we have this channel of fixed. This is a pipeline, and there is some liquid that is flowing with velocity v and static pressure p in this pipeline. I ask you to measure the flow rate q. I know q would be equal to area into velocity. Right? So I need to know the area that can I measure very effectively if I have any diameter measuring device, screw gauge, vernier calipers, or a meter tape. I can measure this area. There's no problem that. I need to know the velocity v. I will know that velocity v. What can I do is I just play with the geometry of this pipeline. I introduce a restriction here of known area. I know the area of this opening, right? I know the diameter or area of this small opening. What will happen at this point? This is point 1. We'll have some velocity, let's say v1 and pressure p1. At this point, the pressure will convert to velocity v2, and there will be some pressure p2 as well. v2 would be greater than v1, we know that, right?
Yes, sir.
So if I apply Bernoulli equation between these 2 points, I would write p1 plus half rho v1 square equal to p2 plus half rho v2 square. p1 would be gone. No, sorry. Right? And I will also know that q1 would be equal to q2, or a2 b2 would be equal to a1 v1, or we can write that v1 equals to a2 v2 by. So it's a very simple principle that we have already discussed while considering the channel flow or the confined flow. Now I know v1 from here, we can put v1 in here and we can just develop another equation for the velocity, right? We have already developed this equation. Can you see this equation here? We have already developed this equation by simply applying Bernoulli equation between the 2 points and calculating the velocity, and we know that then q is area into velocity, so we simply write the velocity equation here. We will directly get the q. All right.
Yes, sir.
So that is a simple flow rate measurement technique, that we calculate the velocity between the 2 points using any restriction, and we can just calculate the flow rate by multiplying the known area of the restriction. There can be 3 types of flow rate measurement devices in a confined flow. One is the orifice meter, the second one is the nozzle meter, and the third one is the venturi meter. An orifice meter is just a simple hole or an opening, that is just a simple hole. The flow will come here, the area will reduce suddenly, so there will be sudden change in velocity here, and decrease in pressure. In the nozzle meter, that the area would be decreasing suddenly, but gradually, but not that much gradual like a nozzle. In Venturi meter, the area of the pipe decreases gradually, and then it starts increasing till it's again equal to the actual area. So this keeps the flow more streamlined. This gives us the better flow rate measurement, because sudden changes in area will induce sudden changes in velocity that would not be like accurate prediction of the flow rate. The actual prediction can be got when we have like right measurement of the velocity at the area change point. So these are the three flow meters. These are the orifice, nozzle, and Venturi meters. And they ignore the viscous effects and the compressibility effects. There is no viscous effects involved in Venturi meter, nozzle meter, or the orifice meter, and there is no compressibility involved. The flow is incompressible and the inviscous. Okay. Is it clear?
Yes, sir.
So how they work, basically, how the flow rate is measured. We measure P1 and P2 using, like if I install a gauge here, now I wrote that Q is equal to A2 into the velocity equation we have find earlier. ठीक है, जो पहले ही हमने velocity equation पहले भी हम find कर चुके हैं, I'm rewriting it here. A V2, which is basically 2 into P1 minus P2 divided by rho into 1 minus A2 square by A1 square. Right? So we know density. If we know what type of fluid is flowing, we can know density. We know both the areas A2 and A1. We can measure P1 and P2. If I install a pressure gauge here, it will give us P1. If I install a pressure gauge here, it will give us, not here exactly, let's say here, it will give us P2. So we'll have P1 or P2, or we can install a pressure gauge like this. Instead of those pressure gauges, I can install a pressure probe here and connect it to a gauge here, and another pressure probe here and connect it to this point. So this gauge will read P1 minus P2, right?
Yes, sir.
So I can have the difference of the pressure as well directly. Is it clear how we measure the flow rate and what are the devices for the flow rate measurement?
Yes, sir.
So these are the devices that are used for confined flow rate measurement. Okay? That is a simple problem that we can solve to understand, okay, how the flow rate equation is used. That we have Venturi meter with a minimum diameter of 3 inches. Let me draw it there. So we have a Venturi meter with a minimum diameter of 3 inches, and it is used to measure a flow rate of water through a 4-inch diameter pipe. Determine the pressure difference indicated by the pressure gauge attached to the flow meter if the flow rate is 0.5 feet cube per second. Let me draw the geometry for you. This is, let's say, this is your actual pipe, which has diameter of 4 inches. Diameter is 4 inches. In this pipe, what you do is place a Venturi meter whose area decreases like this and then come back to this. This is the Venturi meter, and this is your point 2 here, and this is point 1 here. And that's the point 2 is located center line of the Venturi meter, like here. The minimum diameter of this venturimeter is, this diameter is 3 inches. You have attached a pressure gauge from this point 2 till this point 1. Like this. This gauge would be reading the pressure difference between point 2 and point 1, that's P1 minus P2. The question is asking you what is the pressure gauge reading if the flow rate you measured is 0.5 feet cube per second, that is Q is equal to A2 square root of 2 times P1 minus P2 divided by rho 1 minus A2 by A1 square. So this is the flow rate. We know A2, we know rho, we know A1, we know Q. We just simply square it and rearrange it. We will get the value of P1 minus P2, which is equal to P1 minus P2 is equal to Q square divided by A2 square into 2 into rho Q square into 1 minus A2 square by A1 square. Clear? So you can just simply plug in the values and get the required answer. Is it clear that how you'll solve this problem?
Yes, sir.
We'll just simply plug in the values and you can calculate the answer. So that's just done with the flow rate measurement. Any question in this flow rate measurement topic?
Clear, sir.
These are your homework problems: 3.106, 108, and 111 and 112. So all these are different examples related to the flow rate measurement, like nozzle meter, orifice meter, and venturi meter. You can solve them, and if you have any question, we can discuss that. Now, how you measure flow rates in open channel? We have discussed flow rate measurement for closed channels, but what about open channels? Let's say you have a canal like this, and you want to measure the amount of water coming into it, or the amount of water it would be supplying to some farmer in a sub canal or what, where it is. How can you measure that flow rate? For that, we have another apparatus that is called slice gate. Slice gate is like just a restriction to the flow of the water. The water is, let's say, coming at some rate in this canal. Let's say I write it here. This is some river or canal. It is open and you are seeing it from the top. What you do is you insert a restriction in the flow of this canal to a limited point. After that, this canal continues. The flow will stop here, but after that, this canal will keep on flowing. So there will be some velocity V1 here, and there will be some velocity V2 here. Clear?
Yes, sir.
So if you know the pressure and if you can rightly apply the Bernoulli equation, you can measure the flow rate Q for this canal. How we'll do that? Just let me take this picture there so we can discuss that. So what we'll simply do that is We apply Bernoulli equation between 0.1 and 0.2. Okay. So we write P1 plus half rho V1 square plus gamma Z1 should be equal to P2. If you are anytime if you are confused, okay, which terms I should cancel or what terms should be included in my Bernoulli equation, I would suggest you write the complete Bernoulli equation and then you simplify it. Okay, you don't directly write the terms, you just write the complete Bernoulli equation. Like in this situation, I can see that obviously there are some terms that will cancel out, but for your understanding, I am writing it in full here so if you are confused, you just write the Bernoulli equation in full and then you cancel out the terms. Okay, what about P1?
Sir, was pre-sir, sir.
It is atmospheric pressure, so 0. What about P2?
वो भी open ही है ना?
Yes, it is open. Give me a minute. So P1 is 0. P2 is also 0. What about V1?
So relatively कम होगी V2 से वो.
Now in this case, you cannot make V1 0. Why?
सही. ऐसी इतनी कम नहीं है.
Because it's now a canal.
सही.
In free jet case, the liquid was filled in a tank, which was
Stationary था.
initially static, and then it started flowing, so the velocity was comparatively small. In this case, canal is having its own velocity, its own flow, so you cannot make this 0, right? What about V2? You cannot make it 0. That will be much more than V1. What about gamma Z1?
तो given है. अगर हम base को reference लें.
If you place your reference here at the base, so it is given as gamma Z1. And what about Z2? It is given to us, right?
जी.
So we write half rho V1 square plus gamma Z1 equal to half rho V2 square plus gamma Z2. Okay. We can also write that A1 V1 should be equal to A2 V2, right?
जी.
What is A1 here? The width of the gate is B, so A1 would be equal to Z1 into B, right? Into V1, and A2 would be equal to Z2 into B, right?
सही.
Right?
जी sir.
Not A, because A is the opening and Z2 is the actual area. So we will not need to apply the correction here. Z2 into B, if we use Z2 as reference, will not need the contraction parameter. So we can write V1 equals to Z2 V2 by Z1. Clear?
Yes sir.
We can put this V1 from here again into this equation here. We will rearrange this equation to get V2, and then we'll write Q equals to A2 into V2 using this rearranged form, right?
Yes.
That's the same process we have been doing this in this lecture for all the types of the equation. So we'll just put this V1 here, we'll get a V2 in the square root form, and we will put that V2 with the Q here, right?
Yes sir.
So you will get that equation as your homework assignment. You will get this equation as your homework assignment. Okay, and in the next class we will discuss the simplification. You will get some equation of this sort: z2b into under root 2 gz1 minus z2 1 minus z2 square by z1 square. This sort of equation. We'll simplify it we will discuss this next simplification in the next class. Let me just explain it to you. You will have equation resultant equation would be like this. You will get an equation like this when you solve. You should solve it as a home assignment and you will get an equation like this. How we get this equation from this, that we will discuss in the next class. What are the simplifications we are applying basically. One large simplification, we can see that Z1 minus Z2 is approximately equal to Z1. Do you agree?
Yes, sir.
The length of the canal as compared to the opening height, elevation of the opening would be very large. So that would approximately be equal to Z1. So we can simply write this Z1 minus Z2 equal to Z1. Clear?
Yes, sir.
Now if Z2 is, based on this, we can write that Z2 is very, very small as compared to Z1, right?
Yes, sir.
So which means that Z2 square would again be very, very small from Z1 square, right?
Yes, sir.
So Z2 square divided by Z1 square would be approximately equal to 0, right?
Yes.
So 1 minus Z2 square by Z1 square would be equal to 1 approximately, right? So we can write this term equal to 1. So we get this simplified equation. Is it clear?